Hello everyone, myself I am Divya from Department of Chemistry, working as Assistant Professor in Marri Laxman Reddy, Institute of Technology and Management. So in today's session, I am going to discuss a topic that is known as types of corrosion. So we are going to deal today types of corrosion that we have is galvanic corrosion, waterline corrosion and pitting corrosion. Along with this, we are going to discuss one more topic, that is factors affecting rate of corrosion. So how many types of corrosion we have? Like some of the types we are taking here, like galvanic corrosion, waterline corrosion and pitting corrosion. Now we'll see detailedly what do you mean by a galvanic corrosion. Galvanic corrosion will take place in a galvanic cell or a electrochemical cell. So what do you mean by electrochemical cell? An electrochemical cell, it will consist of two electrodes, that is anode and cathode, and it is exposed to a electrolyte solution. Now here we are calling it as a galvanic corrosion. That means it is taking place in a galvanic cell or a electrochemical cell that is having two different electrodes. What I am saying, two different electrodes. So this galvanic corrosion, we also call it as bimetallic corrosion. Bimetallic corrosion, because we are using here two different types of metals, and also we call it as a differential metal corrosion. Okay, the galvanic corrosion, we also call it as a bimetallic corrosion because we are using here two different types of metals in a galvanic cell or a electrochemical cell. So when two dissimilar metals are electrically connected and exposed to an electrolyte, the metal, first going into a electrochemical series, the word meaning, electrochemical series is nothing but the arrangement of metals. Like in the top of the electrochemical series, we are going to have a low reduction potential metals. And in the bottom of the electrochemical series, we arrange the metals like high reduction potential metals. So if you take a electrochemical series, the topmost metals are of low reduction potential metals we are going to place on the top, and the below we are going to arrange the high reduction potential metals in the bottom. So whenever you compare a metals or whenever you are taking these metals in electrochemical cell, so the metal which is in the topmost, will act as your anode because it will be very active. So the top metals, we take it as active metal, and that active metal will be your anode and it will undergo the corrosion. Next, the bottom of the electrochemical series are like passive metals. It will not be active or it will not be reactive. That is why these metals are protected. So this is the electrochemical series. Now what we are telling, the metal in higher electrochemical series. So when we are having a electrochemical series, the arrangement of metals, the metals which are in higher position, lower, it consisting of a low reduction potential metals, and here high reduction potential metals. So the metal higher in electrochemical series, that means which is having a low reduction potential, undergoes the corrosion, and the metal lower in electrochemical series will be protected because these metals are passive, it is not reactive. This type of corrosion we call it as galvanic corrosion. Consider a example or imagine an example that we are taking a electrochemical cell and we are dipping two different type of metals, like one is your zinc metal and the other one is your copper metal. So these are two different metals or bimetallic metals. So here now you can see a formation of galvanic corrosion. So when zinc and copper are connected through the electricity, and also it is exposed to the corroding environment, the zinc higher. See, when you observe in electrochemical series, zinc will be placed in the topmost, like higher in the electrochemical series. So what we have discussed in the before slide, the metals which are in higher position in the electrochemical series will act as the anode. So now in the higher place, who is there? Zinc metal is there. So now zinc metal will be acting as your anode, and obviously it will undergo the oxidation process to get corroded. Next, the copper will be in the lower series and it will act as your cathode and undergoes the reduction process, and it will be protected. So observe here, we are taking a electrolyte solution or any salt solution and we are dipping two electrodes here. One is zinc electrode and the copper electrode. As the zinc is in higher place in the electrochemical series, the zinc will act as anode and undergoes the corrosion. Okay. Like corrosion, why it is undergoing? Because the zinc undergoes the oxidation process. Oxidation means it will lose its electrons. That means when you connect to a electricity, these electrons will move towards the copper. That is why zinc will lose its electrons and it becomes corroded, and the copper, which is a passive metal or the non-reactive metal, it will consume the electrons and it will be protected. So we'll see some examples of galvanic corrosion. Like we can see this type of corrosion in shapes, and also the aluminium shielding in buried telephone cables in underground, and also the steel pipes, Statue of Liberty, and also the stabilizers in aircrafts. This is about the galvanic corrosion. Now we have other type of corrosion, that is waterline corrosion. We have other type is waterline corrosion. So before understanding the waterline corrosion concept, we have to know the what do you mean by differential aeration corrosion. So imagine or take an example that you have taken a beaker and it is filled with the electrolyte solution and dip a metal rod. A metal rod is dipped into this solution. So if you observe the metal rod, the half of the metal rod is dipped in the electrolyte solution and the half of the metal rod is exposed to the environment or the atmospheric gases, that it is in contact with the water. So we have two types now in this metal rod, that is, one is in contact with the water or the electrolyte and the other part of the rod is not in contact with the water. So if you observe this type of construction, so commonly you will see that the part or the metal which is in contact with the electrolyte solution will be getting corroded. That means this part will be corroded. That means it is a anodic part. Okay, so two types of variations are taking place in this type of corrosion. Now we'll see. So imagine you have taken a beaker and it is filled with the electrolyte solution. So half of the metal rod is in contact with the water and it is not in contact with the water. So the part of the metal rod or the electrode which is in contact with the water or the electrolyte solution will have a less oxygenated part. Like that means it is having a less oxygenated and it undergoes the corrosion and it acts as the anode. But coming to the other half of the metal rod, which is not dipped in the electrolyte solution or which is not in contact with the electrolyte solution, will have a more oxygenated and it will be acting as your cathode and it is getting protected. This type of corrosion occurs when one part of the metal is exposed to the different air concentration from the other part. If you observe, the same metal rod is having two different concentrations. The one concentration is high oxygenated and the other concentration is less oxygenated. So if you observe a metal rod, it is having a concentration differentiation. So different aeration concentration it is having. So in that case, it causes a difference in potential between these two differentially aerated areas. A potential is developed between these two aerated areas. Now it is found that the part which is contact in the water is a less oxygenated part. And obviously it will be anode, and more oxygenated part acts as cathode. So corrosion of metals partially immersed in a solution is due to the differential aeration corrosion. So we are taking a magnesium rod partially immersed in a salt solution, that is NaCl. So as we know, a magnesium is a more active metal and it is placed in the higher series of electrochemical series. So the metals which are in higher series will undergo the corrosion and it acts as anode. So in the differential aeration corrosion, we have two types of differential aeration corrosion. Those are, one is waterline corrosion and water drop corrosion. Waterline corrosion and the other one is water drop corrosion. Now we'll see what do you mean by waterline corrosion. It is a type of differential aeration corrosion when water is stored in an iron tank. Imagine you are taking a iron tank like this and water is partially filled in the iron tank or it is half filled in the iron tank. It is found that maximum corrosion occurs along the line. Line means this, okay. So maximum type of corrosion will be occurring along the line just below the water level. If you observe, our water level is still here. So below the water level to the water line, the corrosion maximum takes place. The area. Now we have again here two types or two differential aeration areas. That means one part is more oxygenated part that is not in contact with the water. So this is also your iron metal, right? So now this iron metal which is not in contact with the water will be more oxygenated and that acts as your cathode. Coming to the iron tank or layer that is in contact with the water will be of less oxygenated and will be acting as your anode, undergoes the oxidation process and it gets corroded. That is why we see a maximum amount of corrosion taking place below the water line to the tank. This is how it looks, your corroded part. This is everything of less oxygenated area. This is your cathodic part. This is your cathodic part which is a protected one and it is your anodic part which is corroded. And if you observe, during this oxidation process, the electrons will move from anode to cathode and here the area gets destructed and you can see formation of rust. So in the case of the first step, loss of electrons we see, and these electrons are quenched either by two ways. One is evolution of hydrogen or by the absorption of oxygen, that lead to the formation of corrosion product, and here our corrosion product is the rust. So this is about the waterline corrosion. So we'll see examples of waterline corrosion like a steel, and also the if we pipes and tanks are poorly maintained, those will be damaged by this waterline corrosion. We have one more type in the differential aeration corrosion, that is water drop. From the word we can say, like if you take any metal surface, and on the metal surface if you place a drop of electrolyte or the drop of water, now when this metal which is in contact with the water will be getting corroded. Imagine you are taking a metal surface like this, and a water drop or the whatever the electrolyte solution has fallen on the metal surface. Now the only a surface which is covered by water drop will be getting corroded. Only this part will be getting corroded. And this is your anode. This is your anode. And the remaining part of the metal or the remaining surface of the metal will not be affected, and it is your cathode. So simply, what do you mean by a water drop corrosion? A water drop corrosion is a type of corrosion that occurs when a water droplet sits on the surface. As we have seen on the surface, if you see a water drop, only the surface which is in contact with the water will be getting corroded, and that causes the electrochemical reaction to take place. What do you mean by electrochemical reaction? The electrons will move from anode to cathode by losing of its ions from the anodic site. Hence, the anodic site gets corroded. So the anodic part, the brown one, is called rust. Okay, it gets destructed due to the drop. So imagine a water drop is placed on the metal surface. Only that part we call it as an anode because of its less oxygenated part. And the remaining part will not be affected by this droplet because it is protected, and we call it as a cathode. This is how it looks when a water drop is causing a corrosion on the surface of the metal. Next type of corrosion we have is pitting corrosion. So pitting corrosion is a localized form of corrosion by which a cavity or holes are produced on the material. If you observe or take an example of any surface of the material or any type of material, the material is covered by a protective film. This is your protective film. Like example, you can take something, a paint. Okay, a metal is protected by a protective film, that is a paint. By some means of any hole or any damage to this protective film, you can see a rupture of this protective film. Now, the metal surface in this area get exposed to the atmospheric gases, and here you can see a metal is getting corroded, and slowly by the time this surface is turning into a holes or cavity. This is what you can see, a formation of pit on the surface of a metal or in the metal. You can see here in a metal how you can see the formation of cavity or hole. By this, the metal will be getting corroded. The pitting is considered to be more dangerous than uniform corrosion damage because it is more difficult to detect and predict and design. If you observe, can see a cavity or hole on the surface of the metal. Now this cavity or hole will be of your anode because it is not covered by a protective film and it is exposed to the electrolyte solution, and here your anode undergoes corrosion, it gets destructed or corroded. The remaining part will be of your cathode, that is your protected metal. Now the anode will be losing its ions and electrons. Now the cathode, from the atmospheric oxygen, the oxygen along with the water, it will absorb this electrons and it will produce here hydroxyl ions. This is how a pitting corrosion will take place. So by means of any dust or any damage to the protective film, you can see a formation of a cavity, where in the cavity you can see a formation of rust. And that pit part or the cavity part is known as less oxygenated area, that means your anode. And the remaining part is more oxygenated area, that is your cathode. This is how a pits will look like. So examples of pitting corrosion we have is firearms, gasoline pipes, roof sheets, and also the metal surfaces. Now we have the other topic, that is factors affecting the rate of corrosion. So the factors affecting rate of corrosion is classified into two types, like based on the nature of metal and also the based on the effect of the environment. So based on the nature of metal, we have position in galvanic series and purity of the metal, relative areas of anode and cathode, physical state of the metal, nature of oxide film, volatility, solubility of corrosion product. Coming to the effect of environment, we have temperature, humidity, impurities, pH value, and oxygen concentration and formation of oxygen concentration cell. Now we'll see detailedly what do you mean by each factor that is influencing the rate of corrosion. So based on the nature of metal, we have the first one is position of metal in galvanic series. So if you observe the galvanic series, the metals are arranged according to their reduction potential. That means the metals which are having a low reduction potential are placed in the top, and the high reduction potential metals are placed in the below. So if you are choosing a metal that is from the higher place or the higher position, that metal will be very active and it gets easily corroded. So if you choose the metals from the high reduction potential metals from the below series, it will be protected and it will be acting as your passive metal. That means it will not get corroded. So position of metal is very important when you are choosing a metal. Higher in galvanic series are more likely to undergo corrosion because these are more active metals. When two metals are in electrically contact in presence of any electrolyte, then the metal which is in more, if you observe, if you are taking any two metals, the metal which is a more active, that means the metal which is of higher in position in galvanic series only will be getting corroded. So if you take any two metals and it is in contact with the electrolyte solution, from the two metals, the more active metal only will be getting corroded and it will be acting as your anode. The rate of corrosion depends on the difference in their position in galvanic series. The greater the difference, more will be the extent of corrosion. So this is the position of galvanic series. Like if you observe the magnesium, zinc, aluminium, these are placed in the top of galvanic series and these are more active metals and these metals can easily get corroded. Second type we have is purity of the metal. So if impurities are present in a metal, the corrosion rate is increased due to the formation of a tiny electrochemical cell at exposed parts and the anodic parts are getting corroded. So if a metal is having some impurities, then the metal gets easily corroded, and you can see a rate of corrosion is increased in those type of metals. A pure metal is more corrosion resistant than impure metal. So by this, we have to maintain our metal in a pure condition so that the metal does not corrode. If our metal is impure, the rate of corrosion is high. So zinc metal containing a impurity undergoes the corrosion of zinc due to the formation of electrochemical cell. So when you observe a metal is having a impurity, you can see formation of a tiny electrochemical cell. If you are seeing a electrochemical cell, means there you can see a metals are in contact with the electrolyte and corrosion takes place. Third type we have is relative areas of anodic and cathodic areas, paths. So if you observe, if a metal has small anodic part, imagine if a metal is having a small anodic part and large cathodic area like this, large cathodic area, then in this case the rate of corrosion is very high, because this cathode needs more and more electrons from this anode, and the anode is very small in size. If the anode completely give off its electrons and ions, the anode gets totally destructed. That is why a rate of corrosion is more in this type of areas. And one more we have is, if you take anodic part is very large and cathodic part is very small. This is your anode, this is your cathode. Now the cathode will take only a sufficient electrons from the anode, and now the only some part of anode is corroded or it gets destructed, and the more part of anode is safe. In this case, the rate of corrosion will be less. Next is the physical state of metal. So metals with a small grain size have more tendency to undergo the corrosion. So when the metals are in the small size, it undergoes corrosion. The metals of the more stress strain also undergoes the corrosion easily. Next we have is solubility and volatility of the corrosion product. So if the product of corrosion is soluble in corroding medium and also is volatile, corrosion occurs very faster. Volatile means it can easily evaporate. So next type of factor we have is based on the effect of environment, and here we have is temperature, humidity, pH and the impurities. Now based on the temperature, if you are having a high temperature conditions, then the rate of corrosion is high. If we are having a less temperature conditions, then the rate of corrosion is less. Coming to the humidity, the rate of corrosion increases in the presence of moisture, as we have seen in the wet corrosion, right? So there we have presence of moisture or the electrolyte solution, that is why the metals corrode. So the humidity or the moisture, if it is present, the rate of corrosion is more. Impurities, presence of impurities like carbon dioxide, hydrogen sulfide and sulfur dioxide and acid fumes. These causes the impurities in the metal and it gets corroded. The rate of corrosion is high. Influence of the pH. In acidic medium, corrosion is more, and in the alkaline medium, corrosion is less. These are the factors affecting rate of corrosion.